Hello class, welcome back to Electromagnetics. This lecture we want to continue our review, and this time to a quick review of the electric field. First, a thought for the day, 2 Corinthians 5:7. For we live by faith, not by sight. Which I felt like this was an appropriate verse for a lecture like this because, when you get on the mechanical side, many times you can see what you're dealing with, but some people sometimes have a little bit of a problem when dealing with electrical subject matter. And one is because we can't see it. Electric field, electricity, it's too small or it's in a form that we can't see. So sometimes we have to just proceed in faith and trust the math that it's all going to work out. So again, I thought that was, since we're about to dive into electric field, I thought this was an appropriate verse for that. Again, we're still in part one, so this is the review section of the course, and today we want to just take a quick review of the electric field. Hopefully you've seen most of this in physics class, and hopefully it's not too new to you, but it's not going to hurt to brush up on it. So, electric force observations. So, there was this fellow named Coulomb who conducted experiments related to charge, and from these experiments, he showed that the following items hold true for two charged bodies that are very small in size compared to their separation. So we call this condition point charges. So they're far enough away to where the distance between them is significantly greater than the size of the charges. So the first thing he concluded was that the magnitude of force between the two charged particles is proportional to the product of the magnitude of the charges. So in other words, the greater the charge, the greater the force. Seemed to be a linear relationship there. The next one was that the magnitude of the force was inversely proportional to the square of the distances between the charges. So again, in other words, what this means is the further apart the charges are, the less the force, and it's not linearly related. It's related by the square of the distance. So it drops off pretty fast as you start to move charges away from each other. The magnitude of the force does depend on the medium. So we could have free air or free space, or we could have charges separated by water or by silicone or by a number of different mediums. So we'll actually explore that some in this course, though, that the medium does make a difference on the force. The direction of the force is always along the line adjoining the charges. So in other words, it's like the two charges are both on a string pulled tight between them, and so the force was on each of them would always be in line with that string. There's never any like stray forces or anything like that. And finally, like charges repel. Positive repels positive, and unlike charges attract. So negative attracts positive. So the SI unit for charge was named in honor of Mr. Coulomb, and so the charge of an electron then is known to be negative 1.60219 times 10 to the negative 19 coulombs. The permittivity of free space, which this is the part of the medium that affects the charge, and we'll definitely dive into this a little deeper later, but for now we'll just define this, to trust me on it. The permittivity of free space, which is denoted by the subscript 0, is 8.854 times 10 to the negative 12, and that's approximately equal to 10 to the minus 9 divided by 36 pi. And then the proportionality constant, which was that item number 1, that they were linearly related but by some proportion on the previous slide, is 1 over 4 pi epsilon naught, or the permittivity of free space. So the electric field is analogous to the gravitational field, with the exception that instead of force associated with mass, like the way gravity works, the electric field deals with the force associated with charged bodies. So let's start to look at this then. Let's consider two charges, Q1 and Q2, and let's just say they're separated by a distance r in free space. So if we look at a depiction of this, here's charge 1, here's charge 2, and the distance between them is r. And then we can see this is like that string tied between them, so we define these unit vectors a12 and a21. They're both in line of that string, just one's going in one direction and one's the other. And we'll see that the forces will line up with that same direction here in just a second. So again, make sure we got our nomenclature correct. Q1 and Q2 experience forces from each other, from the charge from the other, and they're designated as F1. So this force here is the force felt from Q2. So this force comes from Q2, and F2, this force here, comes from Q1 onto Q2. So the electrical forces experienced in this case can be mathematically expressed as follows. So here we have F1 is just equal to the product of the two charges divided by that proportionality constant that we talked about, 1 over 4 pi epsilon naught, the square of the distance, and then that direction vector. Likewise, F2 is basically the same thing with the vector going in the opposite direction. With the gravitational field, we define this as force per unit mass. With the electric field, it's defined as force per unit charge. So this can be expressed mathematically as this. So if we know what this force is that's being exerted at a certain point, we can divide that by the charge, and that should tell us what the electric field is at that point. So if we allow this test charge to go to 0, we can notate that in this way, where we utilize from calculus limit as Q goes to 0. So we can now apply this definition to the previous analysis by allowing one of the charges, one of the Q's, to be a small test charge, lowercase q, as follows. So here we have the same equation we had before as F2, except this time Q1 is replaced by Q. So this is the point that's feeling the effects of F2, if we remember back from a couple of slides ago. So in this case, our electric field then will be F2 divided by Q. So in this case, we have the same equation as before, but the Q divides out. So now our electric field is defined as the total charge at point Q2 divided by 4 pi epsilon r squared. So now we can generalize the previous results as follows. Same equation, where the only thing we did here is we redefined this unit vector AR as always projecting away from the charge source. So this is what we call electric field density. So in the future, if we correspond and there is an E in the equation, I hope you don't quote it to me as E. This should always be referred to as the electric field intensity. E, bold-faced E, is always the electric field intensity. So again, if we look at this field from this charge, Q, you can see that it's always emanating out and it's dropping off at a rate of 1 over r squared. So it drops off pretty quickly. So we can now extend this indefinitely. That was for a single charge, but we can extend this to an infinite number of charges if we want, or n number of charges at any arbitrary point P. And so the way we do this then is we take the contribution from each charge, Q1, Q2, all the way up to Qn, and we do vector addition. So all these charges should be in different locations, so that means these unit vectors will be pointing in different directions. So as long as we follow the rules of vector algebra that we've already discussed, we should be able to determine what the electric field intensity is at any point of interest. So here's a graph of what that would look like. So if we had Q1, Q2, Q3, all the way up to Qn, and we're interested in this point, you can see these are the unit vectors associated with each of those, and so we can calculate that and do the vector addition. It should be some force going probably in this direction here, with the quantity determined by, what the charge values of each of the points. So hopefully we've seen all that before in physics class. Now we want to kind of extend this to our sinusoidal fields that we've already discussed. So we can apply this knowledge to the special case of the sinusoidal electric fields as discussed before as follows. So now our electric field intensity is going to be the amplitude or the maximum times this cosine omega t function, this trig function that drives our sinusoid. So in this case, we can determine what the force would be on an electron by multiplying it by E, which is the charge of an electron, times our electric field intensity. And so this results in the next equation. And so the motion of an electron then can be expressed as this. So if this is force, this is the force here, what we have over here, we remember from physics class that force equals mass times acceleration. So this will be the mass of an electron, and then the first derivative of the velocity, remember, is acceleration. So this is our ma equals to this force up here. So if we integrate this out and solve for v, we see that we get this resultant equation and combine some things and put them together and know that we're dealing with just the magnitude of this charge. This is our resultant, and you can see that it is affected by the amount of charge, by the field intensity, by the mass, which in this case is electron, and the frequency. So the higher the frequency, actually the slower the velocity. One thing to keep in mind here is when we did this integration, our constant c went to 0 because we assumed that the electron was at rest before it was subjected to the electric field. So now if we want to extend this further, we can now define some small surface. We'll call it delta S, as shown in this graph here. So here is our small surface, delta S. And we want to consider that as electrons move, there should be some small change in charge, delta Q, associated with some time, delta T. So there should be some charge moving. It takes it some time to go through this space here. So we can mathematically quantify that as delta Q is equal to delta S cosine alpha, and that's just assuming that the area may not be totally perpendicular to the move of the electrons, or may not, which we're calling AX. If it is, then that cosine alpha would be 0, cosine 0, which is 1. And then it's times this velocity and change of time number, and then this is the number of electrons times the charge. So this change in charge over time is the definition of current flow. So again, maybe you've been exposed to this already in physics, but this is a good refresher. And so we can express this now as this change in current flow is equal to the magnitude of the change of charge over time. And so pulling back from definitions we had previously, we'll have n magnitude E, magnitude velocity, the size of our area times the orientation of it with the x-axis. So if we substitute some of our values in from previous definitions, we come to this, and then finally put it in vector form because these are vector quantities that we're dealing with. The current flow itself isn't, it's just a magnitude, but we do have direction associated with the charge and the area. And so as we do that dot product, then that would help us to figure that out as far as how it affects the magnitude going through there. So we know that the dot product that with the dot product, the current is maximized when alpha is equal to 0, as I stated on the last sheet. So this now means that the current per unit area is now equal to Ne squared m omega E naught sine omega t in the AX direction. And so this new J term is our current density, and just to simplify this, it'll be the number of electrons times the velocity. And so again, this J term is a vector. It does have a direction, and so we are referring to this, or we should refer to this in the future as current density vector. So anytime you see a J, a bold-faced J, don't want to hear you call it J. I want to hear you refer to that as the current density vector. So we have the electric field intensity vector and the current density vector. And again, where this is related to the current flow by this equation. So our current density times the area, if we do the dot product, that should give us the amount of current flow. So let's look at one quick example here. We're going to consider 8 point charges that are situated as shown to the right there, all of them one or some variation of 1 unit away from each other. We want to know what is the electric field intensity at each point due to the other 7 point charges. And so by symmetry, if we find it for one, that should be true for all of them. So first, we recall that the field intensity at a point B due to any point charge at another point A is generally expressed as this, and this is what we talked about at the first few slides, just the definition of the electric field. So, if we extend this out between 2 points, we get this resultant equation, and then as we apply it to our specific application, where we have, at points, given points, this would be the general form of the equation to solve this. So if we apply this to our general situation, we'll just go arbitrarily pick, use superposition at the point 1, 1, 1. Our equation then becomes, again, using this general form of the equation here. And this is where we're applying all these coordinates for all the different points here. And so you can see we have quite a few contributions. Should be 7, 1, 2, 3, 4, 5, 6, 7 contributions from the 7 other charges. You can see that they all have different directions associated with their force. So we have to be careful to abide by the rules of vector addition in order to get the right answer here. So if we do that, you can work this out on your own, but trust me, this is what it comes out to. The q over 4 pi epsilon naught, 1 plus 1 over square root of 2 plus 1 over 3 square root of 3 plus the sum of the unit vectors. Again, combining terms and wringing this out, we get 3.29 times q over 4 pi epsilon naught over the sum of the unit vectors over the square root of 3. So again, I would recommend you trying to work through this yourself and see if you can come up with the same answer. If not, just give me a shout out and we'll see if we can figure out what's going on for you.